Well, thank you for coming this evening. Last week we thanked everybody because it was such a miserable night and pouring rain, heavy wind, and tonight it's just delightful. So I know you could be in your yards working or just enjoying a walk on the beach, but thank you for coming and sharing some scientific information with our speaker tonight, who is Glenn Garakowitz. And he's been doing some work on the winter conditions in coastal ecosystems, particularly off of Nauset. And tonight he's going to talk about a river in the sea using an AUV to explore a coastal current. I want to remind you that next week is our last lecture in the series, and it'll be the science fair winners from Falmouth High School and Falmouth Academy, and we'll meet at 4 o'clock to work in with their school day. And it's a very exciting lecture when you see how talented these young students are. So put that on your calendar. I hope that you can make it next week. There'll be 4 speakers, 2 from the high school and 2 from Falmouth Academy. And I've known most of the speakers since they were real little ones. Kevin Lynn, whose father works here, I've known since he was born. And it's just exciting to see this scientific interest in students develop over the years. So please join us next week as well. But without further ado, let me introduce Glenn Garakowitz, who's a senior scientist in the Physical Oceanography Department here at Hui. And he has a lot of fascinating interests in coastal currents, outreach, use of technology, and Glenn?
Well, thank you very much.
We're looking forward to your talk.
Well, it's a real pleasure to be here, and I thank you again for coming out on such a wonderful evening there. I was trying to decide if it was appropriate or inappropriate to be talking about winter processes on an evening like this, but I figure at least I've warmed up after the last cruise finally, so maybe it's a good thing there. And I'd also like to thank the Coastal Ocean Institute here at Hui that funded one of the year's worth of field work there. And I have to say, I've worked on projects in a number of places around the world, and this is my first project that's really been in coastal waters around Cape Cod. And it's been a wonderful opportunity to work with people like Graham Geis of the Center for Coastal Studies in Provincetown there. And I've just been able to meet a lot of wonderful people out on the outer Cape, and also get seasick quite a bit in local waters as opposed to exotic foreign waters there. So this has really been a fun project. The work I'll be describing is work that I've done with my former postdoc, Andre Scherbina, who was a postdoctoral scholar here for 2 years. He arrived the day before we received the autonomous underwater vehicle that will be the star of the show that will appear actually in Act 2 of this. And he departed for the University of Washington about 3 weeks ago, and I miss him already. So the outline of the talk is as follows. I'd like to talk about pathways of fresh water in the ocean and how coastal processes affect the global ocean circulation. I'll talk about a local current system, the Gulf of Maine coastal current. Talk about the observations that we've done on the outer Cape. We initially started out using only the autonomous underwater vehicle, but as you'll see, we've been able to put more and more instruments in the water each year. And then in Act 2, I'll talk about the REMUS vehicle itself. This is a custom vehicle designed for physical oceanography. And of course, it was invented across the street by Tom Austin and his group at the Oceanographic Systems Laboratory. And it was manufactured at Hydroid just up the road there. I'll talk about some of the variability that we've seen in the structure of the outer Cape coastal current in winter. And one of the things I don't recommend for people is if you're learning a brand new instrument like this to start using it off the outer Cape in the middle of winter there. We certainly have lots of sea stories out of this. And then finally, I'd like to broaden the picture again to the larger scale and talk about using AUVs in coastal observatories and being able to measure the freshwater transport across the entire continental shelf. So if we think about what drives ocean currents, there's really 2 major factors. The first is the wind, and that's been studied for a long time, particularly going back to the classic theories of Henry Stommel. But also buoyancy or density differences is another really important driving force in ocean currents. If we look at a popular cartoon of the global ocean circulation, and this is a cartoon that originated from Wally Broker, essentially, there are portions of the ocean where essentially deep water forms, and these tend to be near the polar regions up off of Iceland in the Labrador Sea, and then also in Antarctica there in the Weddell Sea and the Ross Sea there. And essentially cooling and brine rejection from the polar regions makes the water more dense. And if we look at this schematically, the factors that can affect the buoyancy or the density differences in seawater, in temperature, you have heating or cooling, obviously. And cooling tends to make the water more dense and convect and make new water masses. And essentially, the more shallow the water is for a given amount of heat extraction by the atmosphere, the more you change the temperature and the density. And that's why coastal regions are particularly important. If we think about the salinity side or the freshwater side, there's precipitation, there's river runoff, which is tremendously important in the coastal zone. It obviously is collecting the precipitation over a large area. And then also up in the polar regions, there's sea ice melt. And so there's a competition between these different factors in any given area of the ocean. If we think about sea ice melt now, one of the important issues for global warming and climate dynamics is the fact that there's been some pretty clear evidence from satellite observations that the areal extent of Arctic sea ice has been dropping pretty dramatically over the last 20 years there. The most recent rate is, I believe, 7% every 10 years, and that rate is accelerating. I believe as recently as 10 years ago, it was only 3.5% per decade there. And so obviously there's a lot of conversion of the ice into fresh water there. Now, in terms of the overall global circulation, this is important because essentially if you have low salinity, you can actually cut off the dense water that forms in the polar regions, and this is an important climate mechanism that people are very concerned about these days. So essentially this competition between cooling and freshening there affects the entire global ocean circulation. I'll be talking primarily about local processes there, but I just want people to keep that in mind. One of the important areas of research really over the last 20 years is the realization that coastal currents can actually extend over large distances in the ocean. And back in 1989, the late Dave Chapman, in some work with Bob Beardsley here at Huey, actually used some oxygen isotope data to infer that, in fact, there was an entire Northwest Atlantic shelf circulation system, and so that flow essentially comes all the way down from the Arctic Ocean, passes Labrador, the Scotian Shelf, and essentially this shelf circulation really doesn't end until you get all the way down to Cape Hatteras, where the shelf circulation then merges into the Gulf Stream there. More recent work by Paula Frattantoni and Bob Pickard actually shows that there's a very strong current at the edge of the continental shelf, the so-called shelf break front, that's a particularly important feature. And that, too, can actually be traced all the way back to the Labrador Sea there. And so these issues of freshwater transport actually really occur over basin-wide scales in the coastal ocean. In terms of transport, further north, the transport is as large as 1 to 3 sphergips, which is 1 million meters cubed per second there. And 1 sphergip is the equivalent of the transport of 5 Amazon rivers there. That's not the fresh water. That's the freshwater transport itself is much smaller. But it just gives you an indication of the scale of the transport over the continental shelf. Now, if we zero in on the Gulf of Maine region right here, again, it's embedded within this larger shelf current system. A very important feature that a number of researchers here have studied is the Gulf of Maine coastal current. And that essentially runs along the coast of Maine right here and extends past Cape Ann and, in fact, it passes east of Cape Cod. This current system actually splits when we get down near Nantucket, with one branch going around Georges Bank and the other branch into the Middle Atlantic Bight there. And I should say that the freshwater variations within this coastal current are due to runoff from both the rivers in Maine there. There's 4 or 5 large ones that actually feed that coastal current. But again, it's also susceptible to salinity changes in the larger scale continental shelf flow from the Scotian shelf and further upstream. And certainly the St. Lawrence River has a lot of freshwater input, and Hudson Bay is another source of a lot of fresh water there. Now, if we start thinking about the processes involved here when the rivers enter into the ocean, in the northern hemisphere, the effect of the Earth's rotation is essentially to get the fresh water coming out to turn to the right. And so what ends up happening is there's a wedge of relatively fresh water that then travels down along the coast, with the coast on the right-hand side. And in the southern hemisphere, it's actually the exact opposite. The coast is on the left-hand side there. One of the most famous examples of implications of coastal currents actually was on the south coast of Alaska in the Exxon Valdez oil spill. Actually, much of the oil was carried along shelf in the Alaska coastal current there. And so these are pretty persistent and ubiquitous features there. Now, the really important part for the dynamics is that the fresh water, if there's no temperature differences right here, then tends to be lighter. And so we end up with a current that's driven by the buoyancy differences. And again, that's moving essentially out of the board here with the coast on the right. Another phrase that we use, just like in the atmosphere, fronts form at the offshore boundary of these river plumes here, and that's a region of enhanced gradients there. So that's where the salinity is changing very rapidly there, and that's a common feature of the coastal currents. Now, because of the melting of the ice up in the Arctic, there's been a lot of concern about how freshwater transport down through the system might be affecting Atlantic ecosystems. And I'll just say here that when you have low salinity, that affects the local stratification, which is the layering of the density. And that affects a lot of different processes within the ocean. And it also affects again, the circulation. Essentially, the stronger those salinity differences are, the faster you can essentially drive a current there. But it's believed, and it's been shown in a wide variety of systems, that surges of fresh water also affect the abundance and seasonal cycle of phytoplankton, zooplankton, as well as fish populations. And an important example was the collapse of cod in the 1990s. And there was a very nice paper by Green and Pershing just about a month or so ago in Science, and they had a very nice quote here that kind of challenges us as oceanographers. The resilience of Northwest Atlantic Shelf ecosystems is being tested by climate forcing. Predicting the fate of these ecosystems will be one of oceanography's grand challenges for the 21st century. Now, another important reason to be concerned about these coastal currents is that the Gulf of Maine coastal current actually results in a great deal of spreading of harmful algal blooms. And this is a slide here of Alexandrium right here, one of the red tide organisms. And they lead to shellfish bed closings, and we had a particularly bad example in 2005. And here's the area of the federal closure right here. And people like Don Anderson and Bruce Kiefer did a lot of work that particular year, Dennis McGillicuddy. But these processes associated with the coastal current transport resulted in an estimated $30 million economic loss in Massachusetts alone there. So understanding how the coastal current varies then in the face of the interannual variability and the harmful algal blooms is thus very important. So to think all the way back to when this whole experimental program started, before Andre Scherbina came as a postdoc, I was looking through a bunch of satellite images. And so this is essentially a picture of the ocean temperature right here. And you can see the maroon here is 32 degrees Fahrenheit, 0 centigrade. It goes up to about 14 degrees C, 55. You can see this is in February. And there's a lot of other images that look fairly similar to this. But it really struck me how there was such a narrow band of cold water right along the coast. And again, just thinking about the coastal currents, typically we think of in wintertime there being a lot of energy for mixing, both because of the cooling as well as the energy from the wind. The wind can actually mix up the water column pretty effectively there, and certainly we get very strong storms in the winter. And so I was kind of surprised to see such a persistent band here. Thinking back to the slides at the very beginning of the talk, where you get cooling, I had rather naively anticipated that in the wintertime there would be so much mixing that the fresh water would get mixed away. And so that when we see a nice band of cold water like this, we'd actually be creating dense water that could then go out into the Wilkinson Basin right here. And so I was thinking of the Outer Cape as being a really nice natural laboratory to studying the cooling processes there. It turns out that people think that this dense water formation in a lot of different areas like the Arctic actually maintains the stratification in some of the ocean basins. The Arctic is the best example there, and we don't really understand the processes very well by which you create what's called intermediate density water there. And so again, it just seemed to me like an interesting area to study. I also have to say that the people before me had much more common sense about when and where to do field programs, and I think there was a lot of wisdom shown on the part of people who didn't study this area in winter in the past. It's been studied quite a bit in the springtime. So the question that Andre and I wanted to deal with scientifically was what happens to the coastal current in the wintertime. I gave him essentially a hypothesis that the coastal current would be mixed away in terms of the fresh water, and that essentially the shallow area right next to the coast would become cooler and more dense. And so the real question is, what happens to coastal currents when you have both the winter storms, the cooling, the wind forcing? And do you form the type of intermediate water, which is a subclass of dense water formation in general there? And I had done some work in the past on numerical modeling of these types of processes. And you're always wondering when you do computer models of things whether or not those same processes occur in the ocean. So it was a good opportunity to test locally whether some of our ideas worked. So we have now actually, endured is probably too strong of a word, but experienced is probably okay. 3 winter field seasons off the outer Cape. And we've been slowly shifting northward for logistical reasons there. We received this vehicle in December of 2004. And so initially, our first winter, we essentially just ran cross-shelf transects here to see what the variations were across the continental shelf here. And this was down near North Chatham. In last winter, 2005-2006, we actually moved a little bit northward, hoping to take advantage of some collaborations with the National Seashore there. And then finally, this past winter, I won't talk about any of the data in detail. I'll mention it briefly at the end. But we actually moved a lot closer to Provincetown so that we could take advantage of working with some people from the Center for Coastal Studies and using their boat there. I should add, just as a little logistic detail, it takes about 3 hours to get out to this region right here from Woods Hole. And the weather forecasts in winter are not always so great. So what you hope is a 3 to 4 foot sea out here when you leave at 6 in the morning. Sometimes turns out to be 6 or 7 feet there. So it was nice to actually drive out to Provincetown and do our work further north. Now, as I mentioned, the first year we essentially used the autonomous underwater vehicle, the REMUS. And then in years 2 and 3, we've added a lot more moorings, and we really have been reliant on ships. When we do deploy the vehicle, we do have a boat nearby. When I originally wrote my first proposal to work off here, I had the hope that we could just launch the vehicle from the beach. But that turned out to be a fairly naive hope. We at least tried, and we got in our dry suits once or twice. But it became pretty apparent that both the battery life on the vehicle was unpredictable, and the response time, if something happened, if the vehicle had to abort the mission, put the vehicle at great risk there. And so we have been out in boats with all the missions. So this is a time series right here from one of the moorings. And let's see, this is a schematic of one of the moorings right here. This one is in about 110 meters of water. And one of the nice things about this project is that we learned a lot about expendable equipment there. In the wintertime, you tend to lose a lot of equipment with moorings there. And so we at least thought ahead of time about what we could afford to lose. And so the most important instrument on our moorings actually were these small temperature recorders, which are made by Onset Computer Corporation up 28th there. And so the moorings themselves cost about $2,000, and half of it was essentially 8 to 10 of these little temperature recorders there. And because of both the strong storms and the fishing activity, which is still fairly significant even in the winter time there, we were able to absorb some losses on the moorings there. Now if we look at this time series, so this is moving along the bottom in time here from January through March, and this was last winter. And in the temperature scale here, the dark blue is 3 degrees centigrade, and the red is 6 degrees. And you can see that it's, for Outer Cape standards, relatively warm right through the end of January. And then you can see that increasingly it cools. There's a few storms in this time period that actually hasten the cooling there. But you can see that actually the coldest temperatures are all the way back in March. And that's around the time that the heat balance changes sign and the warming is really starting there. So essentially, our experiments really ran from mid-December right on through to March there. And we always wanted to make sure that we had sections when there was the coldest water to see if we could form that dense water. For most of our work, we've been using the Hui coastal vessel, the TIOGA, that's 3 years old there. And it was an extremely nice platform. We worked in up to 7-foot seas out there, which I can assure you was not comfortable, but I think it's a tribute to both the crew, Ken Hutler and Ian Hanley there, as well as the robustness of the vehicle to be able to do sections in 6 to 7 foot seas there. And I think that's one of the really nice things about the vehicle is ultimately it makes things more safe in fairly rough conditions. So now I'd just like to introduce you to the vehicle here. We got this in December of 2004, and we received it from funding from the Office of Naval Research. And the length of it is about 6 feet. It weighs about 90 pounds. So 2 people can handle it and put it over the side of a small boat. It's a little bit more complicated when you're working off the TIOGA because you have about a 4-foot freeboard there. The maximum operating depth is 100 meters or roughly 300 feet there. The maximum speed is about 4 knots, so it can work its way through fairly strong currents there. And the endurance in the wintertime when the water temperature is near freezing is about 30 miles there. The vehicle also got to work off Belize the last 2 winters as a little bit of a break, and I think the vehicle liked that a little bit better, although it was nervous at the time it was chased by a shark. But the range almost doubled when we were working off of Belize there. And to look at it in more detail, and again, this was invented across the street by the people in the Oceanographic Systems Lab. The propulsion and control unit is in the stern. It's got a propeller that goes up to about 1,500 RPM there. It moves it along quite nicely. And what has made a huge difference for us is that it has a GPS system built right into the vehicle there. So it can come up to the surface, get a GPS fix, and know exactly where it is. And it also has an Iridium satellite communication system. It doesn't download the data. It just gives some information on its position and the vehicle state, how much battery life is left. But this is an enormous advantage because just 5 years ago, you needed to put down acoustic transponders in the ocean before there was the GPS capability. And you had to locate them very precisely, and the vehicle would then listen to pings from the transponders to navigate underwater there. And it's been really nice not to have to put out the transponders, and obviously you have to recover them and come back to the same area. And so it's given us the opportunity to really use it large distances offshore and I think much more safely. An important part of the vehicle is its ability to sense the currents above and below. It uses an acoustic Doppler current profiler that measures the Doppler shift of particles above and below, and it can actually see the bottom and measure its speed relative to the bottom so that it dead reckons in between the GPS fixes there. And it has a pretty sophisticated navigation system that Roger Stokey of OSL designed the software for. And let's see, in terms of sensors, there's some optical sensors, a fluorometer that measures fluorescence up near the nose, and also an optical backscatter probe there so that you can see the turbidity. The most important instrument for us as physical oceanographers is what's called the CTD, that measures the temperature, the salinity, and the pressure, and that's slung under the vehicle. That always gets you a little bit worried when you're operating it over coral reefs, but we still have managed to keep it running there. And then finally, a system that we don't use that often, but which is quite useful, is there's actually a side scan sonar on the vehicle here. And we actually worked with Graham Geist to look at blueberry rocks off the outer Cape to look for boulders and relative rates of shoreline retreat there. But essentially, the side scan sonar is really why this vehicle was initially developed, because it's widely used in Navy minesweeping operations now. There's all sorts of very sophisticated work being done now with these vehicles actually working cooperatively. So in other words, one vehicle can tell another vehicle, oh, there's a possible target over here. And it's really quite amazing, all the different things that are being done with the vehicle now. Okay, and then finally, it really is remarkable the range of boats and ships I've actually worked off with this vehicle. The first one actually was my sea kayak. This was our very first mission in Ashumet Pond right here. And we actually launched the vehicle from my sea kayak. I think it was December 28th. I know it was between Christmas and New Year's there. And it did a mission in Ashumet Pond there. It's also been used out of a John boat off of Barrow, Alaska, a torpedo recovery boat off of Hawaii, and some not so well-maintained boats in Belize as well there. And it really gives you the opportunity now to do field projects much more economically. My other projects, for example, might involve larger ships that cost $15,000 to $20,000 a day. So it's really great to be able to call up a harbor master and say, hey, would you mind taking us out for a day or two? The economics of that are really great. Okay, and so this is a typical REMUS section that we took off the outer Cape, and this is the salinity right here, going from 31.9 parts per thousand, or practical salinity units, up to 32.5. And the vehicle, you essentially program emission into it before you throw it off the ship there. And it's relatively easy to program there. I made the decision early on not to use people from OSL, engineers and such, but that we should try operating the vehicle ourselves at all times. And while that led to some stressful situations on occasion, we could always make the phone call back and say, oh, things aren't working right, and get the nice ideas on how to fix things. But the great thing is you get high resolution in both the vertical and the horizontal there. If we had taken a normal ship and just dropped an instrument over the side, a typical CTD there, it would have taken 40 typical stations to do this. And a typical section like this, this is 15 kilometers, so 8 to 10 miles there. That only takes 2 to 3 hours to do there. And so it really is a huge advantage for us. And then, of course, we can contour it in very nicely and create some pretty nice fields here that show the gradients associated with the coastal current. Now, this is one really nice realization here from February 2005. And for this particular case, the wind was blowing from the southwest, so the fresh water actually was moving offshore. The rotation of the Earth tends to make the surface layer move to the right of the wind. But what I want to point out is that, again, the vehicle has that acoustic Doppler current profiler on it, and so it's actually measuring the currents the whole time it's out there as well. And this is the along shelf current right here, and the darkest blue there is 30 centimeters a second, which is about 0.6 of a knot there. And you can see it's offshore. It's about 8 kilometers offshore right here. It's centered right above this gradient zone right here within the coastal current where the gradients intersect the bottom. And it's relatively narrow. It's only 3 to 4 kilometers wide there. And so essentially that's the highway that for example, the Alexandrium red tide organisms actually can ride to the south on there. Now, I have to say, again, I was really surprised. I was expecting to see things relatively well mixed and for there to be primarily temperature gradients in the shallower water. But the persistence of the coastal current, again, was a surprise to me. Now, the vehicle also contains a fluorometer, and using some calibrations, you can actually convert that into chlorophyll A concentrations. And while we haven't looked at this data quite so much, we did have some nice data from that February 2005 data set showing the highest levels in the early bloom there actually being in very shallow water. Just in about 10 meters of water. And then you can see a layer extending further offshore here. And then finally, another example of the sensors. These are bed forms at the bottom viewed from the side scan sonar on the vehicle. And this is about 80 feet in this direction right here. And you can see that this is a region where there's really large gradients in the ripple size right here with fairly large ripples here. Those might be 1 to 2 feet. And then that's right next to a region of much smaller ripples there. So to put in a nutshell what we found over the 2 years, this is a series of sections right here in terms of the density field. So I've been showing salinity a lot before. But this is the density evolution last winter from 2005-2006. And what we can see is that these are the lightest densities here in the reddish. And as we get out to the green here, that's more dense water right here. We can actually see a tremendous amount of variability in the density fields right here. There is a coastal current. You can see that there's relatively weak density gradients right here, and this is like that wedge cartoon that I showed at the beginning. By March, when the river runoff from Maine starts to get fairly strong, we can see that there's much stronger density gradients, and the current is accelerating here. But in terms of the variability, it turns out that the wind forcing becomes very important in the wintertime. And last winter, the times that we were able to get out, the winds were from the southwest. And this tends to push the lighter water in a thin layer further offshore. And so in these two particular cases, the wind was not very strong at all. And so we had the normal buoyancy-driven situation there. But one of the things that we've been investigating is how important the response to the wind is. Again, I had thought before we started the whole project that there would be enough energy from both the cooling and the wind to wipe the coastal current out. But most importantly, there's never really any time where the cooling actually creates dense enough water to move offshore. And I won't go into the more complicated results, but essentially in the wintertime, the cooling is important at the very edge of the coastal current. And so you still get relatively cool water masses there. But the coastal current sets a new boundary at which the more dense water can actually form there. And what's interesting is it's analogous on the larger scale to what Bob Pickard has found in the Labrador Sea. When he gets cooling, there's the shelf break front at the edge of the continental shelf, and he finds that the densest water forms, the coldest water forms, just seaward of that shelf break front, and we have a smaller version of that here off of Cape Cod. So the coastal current ends up becoming very important in controlling the density that's created from the cooling processes. One of the things that we've tried to do is get the data online from the REMUS sections within about a day after going out. And I know Andre received emails from several fishermen, I guess particularly cod fishermen, are interested in the bottom temperatures there. And so all of the sections from the last 3 winters are on that website that Andre put up there. And now to take that big step backwards again, I mentioned earlier that we were able to operate the vehicle in up to 7-foot seas, but a larger issue is, do we really need to be out there? This was from our first deployment. After this experience, I would have said no. We don't want to be out there. We have been working to try and come up with conceptual designs for coastal observatories to study the freshwater transport problems. And right now the National Science Foundation has an Ocean Observatories initiative that has global, regional, and coastal components to it. And there are cabled arrays that are called endurance arrays that will hopefully measure the ocean over 30-year timescales. But then what we've contributed from our experience working with the REMUS AUV vehicles is what's called a Pioneer array that can be a mobile array that can move around to different areas and study coastal ocean processes. And that doesn't use a cable. We are hoping to get an observatory at the shelf break south of New England, and it would consist of a number of moorings there, on the order of 10 moorings, to study that freshwater transport on the larger scale, extending across the whole continental shelf. And a really critical element that OSL is working to develop right now is a self-powered mooring with a docking station. And so using the same type of Iridium satellite communication system that would be up at a surface buoy, OSL has been working with Navy funding to produce docking stations that the vehicle can actually go in. We'd like to ideally have it self-powered by wind and solar there, and have moored vertical profilers that would go up and down through the water column several times a day and measure the changes in the stratification. We're very interested in how larger scale climate signals like the North Atlantic Oscillation affect the type of smaller scale cross-shelf exchange processes that moves the fresh water offshore in particular there, so that we can understand when we do have freshwater pulses from the north, how much goes along the shelf and how much goes offshore to prevent deep convection. And then the proposed deployment sites would be up in the Mid-Atlantic Bight south of New England there. So just to wrap up here, coastal currents are very important in terms of both the circulation and ecosystems. And one of the really important results of the last 10 years are that coastal currents are even capable of connecting ocean basins. They certainly affect both climate through the modulation of the dense water formation process, as well as ecosystems in terms of harmful algal blooms, as well as primary and secondary production. And they're really a tremendously variable and dynamic environment. I've shown you individual sections, but when we were out just a month ago, we were working again near Provincetown, and we did another section just off of Nauset Marsh to repeat what we had done the previous winter. And it was remarkable how different the two sections were there. And so while we've been concentrating on the first phases of this project on just understanding the cross-shelf structure, there's clearly eddies and other features that are important. And so we'll need these vehicles in the future to study some of these smaller scale motions. Another interesting thing, when you're out there year after year, you see some really peculiar differences. We had not seen very many marine mammals our first 2 winters out there. This past winter, we saw one pod of 100 common dolphins off of Race Point shortly before Christmas there. And I guess there were a couple pods running around here in January there. And then just when we were doing the section just a month ago off of Nauset Inlet, there were about 12 right whales out there actively feeding. And so it was really amazing to see so many right whales, just knowing how few of them there are. And that was a wonderful experience there. So I guess my final comment here is that the new technologies really allow us to study the coastal circulation on a wide range of scales, extending really from the basin scale in terms of that freshwater transport to the local scale from the rivers. And if anybody does want to work off the Outer Cape in winter, definitely wear lots of warm clothing. And I'll stop there. Any questions? Yes?
Is the REMUS dives?
Oh, yes. When I showed the triangles there, it's going from about 4 feet from the surface to about 4 feet from the bottom there. So we're getting the whole water column there. And that's what's so great in terms of seeing the structure. You can really see the gradients very clearly there.
How does it dive?
It has these fins back here. And so there's the control system. You can actually see it when you launch it. It's faintly positively buoyant. And then the propeller starts spinning. It makes the rooster tail. And then you can see the fins turn. And it normally dives into waves. It likes waves to dive into there. But I should add that they now have different REMUS vehicles that are capable up to 6,000 meters. And that one has a titanium hull. But a model that I'm very interested in for that observatory is the REMUS 600 that can go down to 600 meters depth. And that has a range of about 200 miles. And so I would say these vehicles are truly revolutionizing our views of the ocean there, because we can really measure in ways that we could never measure before. Yes? Okay. So if we're on the ship, we have a laptop computer, and we used to hook cables into the vehicle, but just about 2 months ago we got wireless on the vehicle. And so we edit a file. It's called the mission.ini file, and we then send it over to the vehicle with the wireless there. So it's now programmed with that mission. So we then launch, we just drop it in the ocean, and we have a little hydrophone transceiver. So when it's in the water, we send out a message that says, "Start your mission." So it knows where to go, and so it takes off. It does its mission. And we listen to it on the hydrophone transceiver there, and it actually gives its estimated lat long. So it really is incredible. And we're working with people in the Applied Ocean Physics and Engineering department right now. They're actually putting hydrophone arrays on the back of these so that the Navy can listen to whales or listen to large metallic objects underwater there. So they're being used for a real wide range of applications. But I think it's really significant that I'm not an engineer. I didn't help develop the vehicle. It really is a tool for scientists now there. And again, I just take physical oceanographers along, and we just operate it there.
What is the value?
That's a good question. It's more than my house. It's the base model for this was $320,000 there. So that's why, when I was originally thinking, oh, let's just throw it off the beach, I was just really not thinking about all the different things, that go into possibly aborting a mission there. The REMUS 600 is about $700,000. But if you think about the economics there, if you're paying $30,000 a day for ship time, that's 23, 24 ship days there. And, there's things that you can do with this scientifically in terms of the sampling, running 2 meters above the bottom. That's very hard to do when you're towing an instrument there. So it really is a whole new way of sampling the ocean there. Yes?
What did you say was the range of the 200-meter capable REMUS?
Let's see. The 600-meter capable REMUS is 200 miles.
200 miles.
Yeah.
Is Tom Austin still involved?
Oh, yes. Yes, he's heading the group there. Yeah.
Is it battery operated?
Yes. Yes. Yes.
Give us a broad statement about what the objectives are of your particular institute, Oceanographic, as compared to the coastal or the weathering and various institutes.
We're a research and education institution there. So we want to understand how the ocean works there. And we don't directly get involved in any advocacy roles in terms of policy. We're a scientific organization there. We, for example, that coastal observatory that I talked about, that's for research purposes, but we hope that that NOAA will actually pick up a lot of the technology that we're using to do ocean observing systems that will help forecast the weather and forecast oceanographic conditions there. So we work very closely with people that do forecast the weather, that do try and predict ecosystem events and things like that there. But we focus on the research there. Yes?
One of the things you said at the beginning was that the transport of the cysts for the red tide blooms were in this coastal current.
Yes.
You showed a slide, and if I understood it correctly, the turbidity data that showed that the bloom was occurring very near shore in less than 10 meters of water.
Yes.
But the same, or the next slide showed that the current was actually
Much further offshore. That's true.
So,
That was phytoplankton and not the red tide organisms there. And I should also distinguish what's interesting about these jet systems, which has been one of my main areas of research there, is the fact that if you get in the jet, you can have very short transport times, very long distances down shelf. But if you stay locally there and you don't get involved in the front, you can actually have a very long residence time in one area. So it's a very good question. Essentially, in that cross-shelf section of the chlorophyll A there, that the phytoplankton near the beach is probably going to stay around there, whereas organisms that might be, say, fish larvae or other things that kind of want large dispersal, if they can get in that jet, they can travel over huge distances there. And I think that that's a really general problem in coastal oceanography, is understanding local retention zones versus these really long currents. And one of the best examples I've seen of how long particles can be transported is there was an experiment here done by Dick Limeburner and Bob Beasley, and they launched, I think it was 120 drifters north of George's Bank, and something like 80 of them ended up near Cape Hatteras. So it's remarkable, once particles can get involved in that jet you know, they can go huge distances and have a pretty coherent trajectory there. But also, you know, if you don't get into that jet circulation, you can stay in one area for quite some time. Yes?
I have two questions. The first is, does the coastal current lose integrity near Nantucket Shoals? Because there's so much.
That's a very good question.
And the second one is there anything, any analogous research to yours going on, say, in the Hudson River area or off the coast?
Oh, yes. Let's see. Nantucket Shoals is an interesting area because the tidal mixing is so great there. And so what happens is that is an area where the mixing is large enough to remove some of the gradients. And so what actually happens is, I believe that the flow skirts Nantucket Shoals. And so the area between the well-mixed area and the stratified area actually is a tidal mixing front. And so my guess is that the coastal current then merges smoothly into that tidal mixing front, which then can go around the Muskegon Channel. And it's remarkable, again, with our local waters. I think some of these details of how the different current systems connect to each other aren't well understood. And in particular, how conditions might change where particles might jump onto a different track. I think is an important aspect for the future. Now, people are working off New Jersey, and they have a nice observatory there at Rutgers University. They call it the Cool Room, Coastal Ocean Observing Lab. And they have a room where you can see all the satellite images. And what they've been using as an autonomous vehicle is a glider. And that changes its buoyancy, so it does the undulations up and down, but it only goes at 25 centimeters a second, and this goes up to 2 meters a second. So that's why I chose this particular vehicle, because I know it can get across those strong jets that I like to study there. But I was actually involved in a big experiment this past summer with Rutgers, and they had a huge rainfall event the month before we went out. I think it was the 5th largest in the last 120 years. So the Hudson stream flow was enormous. And we saw all sorts of fresh water that got all the way out to the shelf break. And that violated my Coastal Oceanography 101, which is that everything follows the isobaths. But there was so much fresh water that it basically blew out over the whole shelf. And it had some interesting operational implications, because when Rutgers runs its gliders, there's a very delicate balance. You need to ballast the gliders. So they used a climatology from the previous 3 years of study to set the ballast when they started the experiment. The water in the top 20 meters was so light that the glider couldn't penetrate. So it was a density that hadn't been experienced in the previous 3 years of weekly observations there. So yes, people are studying these coastal current systems in a wide variety of areas there. And the real critical thing is these vehicles let us see under the surface. And so much of our understanding is really from satellite images. And the problem is that if you're looking at ocean color, you're seeing the top layer. You could see from that chlorophyll picture that it's down at 20 meters depth where the local maxima is. And so, you know, in the same way that I think the first satellite images made us realize, wow, there's eddies everywhere, I think that this is going to change a lot of our ideas about how the coastal ocean processes work there. Yes?
Do you think there's even a future for anchored instrumentation on the continental Colorado Shoal?
Oh, yes. Oh, absolutely. There's always going to be the need for the fixed moored platforms. And one of the things that I didn't talk about here are processes like internal waves and internal tides. And they ride on the interface between layers in the ocean there. And it's very difficult if you have a vehicle that's moving around and it's going through wave packets, for example, to figure out what the structure was. The vehicle is moving, the currents are changing. The best way to study those processes is definitely with the fixed anchored moorings there. So I think that'll always be in the oceanographer's toolbox. Yes?
You had a
Yes.
and as it approached the Gulf of Maine, did a 180 and went right back up.
Yes.
What causes that? I mean, how did that all of a sudden change?
The simple answer, without getting too complicated, is if you go all the way back to the conservation of angular momentum, things like to stay at the same isobath. If there's not a lot of stratification, it wants to remain on lines of constant depth. And so because the Gulf of Maine has the big central basin, the flow actually turns in. But what's interesting is over the continental slope, as you get deeper, the isobaths don't connect into the Gulf of Maine. There's a sill depth there. And so the slope flow actually separates, with part of it going into the Gulf of Maine and part of it continuing right on down to the Mid-Atlantic Bight and ultimately Cape Hatteras there. But that's what I was taught when I was in graduate school, is, you know, things follow the isobaths there. And I think one of the really exciting things now that we're seeing from these different vehicles is, just like the example off New Jersey with the Hudson River, there are times where the forcing is so large that it has just a total change in behavior of the system. And I think that's the real exciting part of looking at the coastal variability there. Is, you know, when does the whole current system totally change its behavior there? So, well, thank you for coming out on such a beautiful evening. Also, if anybody wants to look at the vehicle, you know, I'll be happy to show it to you in more detail there.